Okay, I want to walk through a bunch of examples with operators and take a look at how they work. The first one of these examples is just an addition and a multiplication. And the reason this example is here is because it reveals something about how this is going to work. So if I just go and run this, and I walk through setting the variables, they do what you'd expect. You get this, you get an answer 14. And we'll print that answer out. We get x equals 14. So it calculated something. Now the question is, did it do a plus b and then multiply by c, or did it do b times c and multiply by a? It did the latter one of those. It did the multiplication first. So b times c is 12 plus 2 gives us the 14. And if you want it to do it in the other order, then let's go back and edit this code. Then you're going to have to use parentheses. And the parentheses are going to force it to do the addition first and then the multiplication. So if I just run this code, you'll see that now I get 20 because 2 plus 3 is 5, 5 times 4 is 20. And the thing that you should take away from this is the fact that there are some automatic precedence rules of what goes first inside Python code. And these apply to more than just addition and subtraction. There are a whole bunch of things that you probably don't think of most of the time as operators, but they are in Python. The key to this is that there is a table of precedence, and we'll take a look at that table of precedence, and then we're going to play with some of the other operators. But yes, there are rules. These are taken from algebra, and they are the order in which things by default will happen. The best way to deal with computer language programming precedence rules is when there is doubt, use parentheses so that you explicitly tell the human beings which order you want things to happen in. And that prevents all sorts of confusion. The computer isn't confused. It calculates something. It doesn't mind applying precedent rules in ways that you would never expect. But if you explicitly put in parentheses, then you and every other person that reads your code will be able to look at it and say, this is the order this happens in. This is why this happens in this order. Now I've taken the table of all the operators and all the precedence rules out of the Python documentation and duplicated it here. And the things to take away from this table is you'll notice that when it says parentheses there, grouping, that's the highest precedence, which allows you to control all the others because it is the highest precedence. This f-args is how you call a function, which means that if you have a function somewhere there and it's grouping a bunch of things together as the parameters, that stuff is going to happen before it tries to use the value from the function, which makes some kind of sense. Now, most people just glancing at this wouldn't realize that this is an operator, but the square bracket for indexing into a list, indexing into a dictionary, getting a range of values out of a list, that is an operator, and its precedence is higher than other things. That way you can have a list of integers that says 1, 2, 3 in it, and you can say, call that list x, and you can say x sub 1, okay, plus 2. And it's going to do the sub 1 before it does the plus 2, which makes some kind of sense. The next one that most people don't realize is an operator is the dot operator when you call something. We've been working with objects, and we've said some object name dot a function. That's an attribute of the function, and that is higher precedence than the other calculations. So it's just like indexing into a list, indexing into the members, the methods, the attributes of a class is a higher precedence than other things. Now, I just realized this. Something is not quite right with my table here. That should have 2 stars right there. I will fix that before I send it out to you. But that should say star star from exponentiation. And exponentiation is a higher precedence than other mathematical operators. And I would classify all of this stuff from exponentiation down to bitwise OR as all mathematical operators because they do something to numbers. And the next highest one is the bitwise not. Bitwise not takes the values and flips all the zeros to ones in bits. So that's a pretty high precedence operator. And after that, we have positive and negative. Like when you put in the number -3, Python doesn't look at that as a number. It looks at it as the operator minus followed by the number 3. And you really want to group those things together. Okay? So yes, you can have an expression like -3 plus 2. Okay? So you want strong grouping between the -3 part, and later you do the +2, which is way down here at addition. Now, multiplication operators, this is star, slash, and modulo, okay? These guys are multiplication division operators. Again, I'm missing a star right there. I will fix that. Those operators are all happen before addition and subtraction, and we're going to go through examples of these bitwise shifts, the ands, the XOR, the OR operators here in a little bit. Then we get down to the Boolean and the comparison operators, things like in, less than, not equals, equals, and other Boolean operators like and OR, which says if I want this and this to be true in an if statement, that happens way after other things. So this is the entire table of all the different precedents. Now, magically in the middle of the lecture, we fixed the exponentiation operator in this, and also the double slash, which is the integer divide. And we're going to actually give it a try to run this example with a arithmetic shift operator. Let's visualize this. And first of all, we're going to set our variables just like we did before, 2, 3, and 4. Now, when we do shift 3 positions with a number, that's going to multiply by 2, 4, 8. So it's going to multiply by 8 when we take a and multiply by 8. So what I would expect to see is that we get a, which is 2 times 8 is 16. Now, the reason for this arithmetic shift left instead of just multiply the value is in some context, this makes a lot more sense. If you're trying to manipulate a binary value for some reason, and you're shifting it to a particular position, it's much clearer in the code. The second reason is that this tells the system, the Python system, your exact intent. And the shift operators are implemented in the underlying machine in very efficient fashions. In fact, they're implemented in a sufficiently efficient way that in some ways it's better to do this kind of a shift for performance. Now, generally speaking, when you write a program, you don't care that much about the performance. But let's say you're doing something where you really have to have some very specific multiplies happen and they have to be really fast. And you're doing it on very limited hardware. For example, I worked on taking the floating point calculations for hearing aids some 20 years ago and taking out all the floating point calculations, which are incredibly slow, and replacing those with calculations on integers using shifts to make it work so that these hearing aids weren't the size of a desktop computer. They would actually fit in people's ears and run on batteries that were sufficiently small that they only had to change the batteries about once a week. And that's why being able to take some of these operations and put them into, this is specifically what I want to do and what I want to make the machine do at this point so that it's efficient can be really important. Now, most of the time these days we work on laptops that have vast amounts of compute power. And we've got lots and lots of compute power everywhere. I mean, good heavens, you can go to Walmart and you can buy one of those musical little playing cards, open up the card that sings Happy Birthday, and goes, Happy Birthday to you. And that little card, okay, with the terrible Happy Birthday song in it, okay, that's kind of ringy and kind of ugly sounding, but it plays, right? And you buy it for what, $1.20, I think it is for one of those cards. It's more expensive than just a regular card. But you open it up, it plays music. I'd like to point out that that card, okay, that you buy for $1.20 has more compute power than we used in 1969 to put astronauts on the moon. So you've got lots of compute power, but at the same time, sometimes you don't have all that much compute power. The computers that you use inside lots of devices don't have a lot of compute power, and they may not have hardware to do floating point, and you may need alternatives at some point to say, yeah, I've got this particular algorithm, and the way it's implemented isn't going to do it. I've got to be able to use some of these operators, like the shift operator, which is the one we just did an example of, and actually make the code faster. So the shift in the other direction is divide. So let's go back and edit the code, because if you can multiply, you can also do a divide. So let's take C here, and let's do the other shift. Let's shift it by 1 position. So it should end up being 2 when we run it, and we will take this and run it, and we start out with our variables again. And this time we're taking C, which is 4. We're shifting to the right, which should do a divide by 2. So I would expect to get 2. And X comes out as 2, and it prints out as 2. So that is, when we look at our table of operators, that's the shift operators. Now the AND, the exclusive OR, and the bitwise OR all work on things to give us access to the bits inside something. Because remember, what we see as a decimal 2 is really represented as a bunch of zeros, a 1, and a 0 in binary. So let's take a look at some of those operators. Let me edit the code real quick here. And let's say something like C and Python has the ability to do numbers in hexadecimal. That's base 16. If I do 0x1, which is 1, okay, we should see that this is C and 1, which is going to be 2 1s in different locations inside this 4, and it should give me a 0. So if I visualize this and run it, okay, I get a 0. Now if I go back and I edit the code and I say, what I really want is want to do a 4 here, okay, so that these are going to be the same. This is a 4 and that's a 4, so 1 bit is the same. Let's actually change this so we can see what the effect of having 2 bits turned on. So this value in binary is 000101. That's the 0x5. And the other one, and C, equals in binary 000100. So it's got a bit that's in common. That's that individual bit right there. And it's got a bit that isn't in common. So when we get done ANDing them together, each bit is ANDed together at its position. So I'd expect to get 4 out of this. Now let's go there here and run it once, and we get 4. And you go, well, what would I ever want to use this for? Now, let's suppose that you're working on a piece of software that controls some piece of machinery, and that machinery reports values back to you. Let's say that it reports 14 hexadecimal back to you. And you go, what I really want is I want the 4 out of there. Okay? So I'm only going to AND with the bits that I want. And I know that those bits in C, okay, are 10100. That's the binary version of C. So I want these bits to be pulled out because I've got just this little piece of information coming back from this machinery. And that other stuff I want to throw away. So all I have to do to just get the least significant bits is I just AND it with a 7. Now, 7 is all 1s. Okay. So we have this with 3 1s. And 1 and 1 is 1. So I got that bit out. 1 and 0, that's the next one over, is 0. And 1 and 0 is 0. So if I go and visualize this and I run it, okay, I picked out the 4 out of this hexadecimal 14. So this is how you extract a few bits from a value, is you AND it with something. Now let's say that I want to pick out the 1, okay? So I want to do some other thing that picks out that 1 value. What I want to do is, let's make another variable here, and let's say y equals C and 0x. Say I want a bunch of bits at that position, and then I want to shift it over 4 positions so that I get it printed out. All right, so what I'm going to do is I really want to get these other bits out of here, the bits up here that are where the 1 is, and I want 4 of them. So I've got F, which is all 1s. So this is going to end up being that value. And everywhere there's a 1 in this value is where I'm going to pull data out. And C is the same value as I had before, so it's going to take this and it's going to have these bits right here are the ones it's going to pull out. Okay? Which is just going to give me a 1, but it's in the wrong position. I've got it moved over as a big number, so I want to take it when I get done, and I want to shift it over 4 positions to get it so that it is the values without it being multiplied by something else. So let's visualize this. When we get done, we've pulled out a 1. Now, a different example of this is, let's say that this value has changed to a 7 over here. Now, what I'd like to get is that 7 out. So if I go and visualize it and run it, okay, I can pull the entire 7 out and get it as a 7. So you notice it's not 7 times a bunch of things. It's 7 when I get done. So I can pick out pieces of numbers. Now, similarly, you can use OR to put in pieces of numbers. But each one of these bitwise operators gives us the ability to go in and take something and combine it, pull it out of a number, get some piece of data out. Probably the best example that I know of picking out values out of numbers is there is this ancient programming language called COBOL, and it has built into it a packed decimal value. And each digit in decimal is stored in 4 bits. So every time a calculation happens, what COBOL does is it wants to go out and take out this little chunk of 4 bits of a number, do a calculation on a digit, okay, and then the resulting values it's putting back into the middle of other values. Okay, and you go, who cares about this? COBOL is commonly used in banks because it has exact calculations for finance. All these other things work in binary, and they don't give you exact results. So, you know, when you calculate out a mortgage for the interest for buying a house, you want that to come out not sort of right in 30 years. You want to come out exactly right in 30 years. So this ability to go in and pick out pieces of values, work on them, put them back in, it's very important to get some things to work right. And yeah, we could do this in other languages, but you end up doing all of these operations that look like this. They're difficult to do, and consequently most banking software to this day is still written in COBOL, so that it can take advantage of packed decimal values and do exact calculations. And that's the underpinning of large portions of the financial services banking industry, is these ancient programs in this ancient language, because it makes it convenient to work on little bits of values at once and get the right results. Okay, I owe you one more example on how to put a value in. Let's say that I want to change that 7 to something else. So instead of doing this, we will make this an OR. Okay, I have combined a whole bunch of things in here. And this is the kind of a thing that you would see if you're going to put a value into a number. The first one is I'm going to put in B, which is a 3, into the middle of this other number. And I only want 4 bits of it, which means I've taken it and I've ANDed it with 0xF so that all the other bits in B get thrown away. It's just the least significant 4. Then I've moved it over 4 places so that it's going to be in the right position to go inside this hex number. And I've done that with a shift. Now, the original hex number, C, I want to preserve the 4 that's in it. So I don't want to lose these other bits over here. So I'm going to AND it with just the place where I'm going to stick in the new value. That's right there. That's zeros. Everything else in it is F, so that it's all 1s, and 1 and 0 is a 1, so it keeps the values in C. And then I've ORed the 2 together. So to print this out in a fashion so you can understand it, I'm calling this function hex, which converts a value y into its hexadecimal representation. So let's visualize this, and let's go through and run it. And at the end, you see I have 34. I started out with 74, and I took away the 7, That was right there. Okay. I kept I took the B, which is the 3, shifted it into the right position, and in the end, I got 34. So here's how you put a value into the middle of another value. And as you can see, this is not a pleasant expression to read. It's got a lot of stuff going on in it. But if you know this kind of an expression, test question hint, if you know this kind of an expression, it's pretty obvious what it does once you've gone and said, okay, I want to take this value and I want to stick it into another one. Or I want to pull a value out, test question hint, and be able to pick out a value out of another one. So we are going to have a homework exercise that covers some of this because, yes, these are going to be on your final to actually manipulate some of these things and answer some basic questions about operators. But I also think that at this point, you have a table of operators, okay? We've gone through most of them. I don't think I did an exclusive OR. I did that on the light board outside. And I've done most of these other operators, so you've actually seen most of them at some point. There are a bunch of ands in the current homework, but I think what and does is fairly obvious. If you've got an if and you've got two conditions you have to have at the same time that both have to be true, then you use and. If just one of those conditions has to be true, you use or. There's at least one lambda or one expression in here that I haven't talked about in the whole class, which is lambda. And I don't think we're going to talk about it in here. We've used it a little bit. You don't realize it. But when we did list comprehensions, we actually used it. And it's something you will use when you do list comprehensions, but you generally don't see it a lot outside of list comprehensions. So we have used it, but not much. And it just kind of naturally happens when you do a list comprehension. It isn't something you have to think about. If you want to know more about lambdas, you use them a whole slew in functional programming. Now, that's kind of the operators. The next stuff we're going to cover in this class is really going to be the start of working on our game and how we use stuff for machine learning. But this gives us enough operators that, yeah, we can do most things. We know how to subscript. We know how to pull lists apart. We know how to put things in lists and dictionaries. We've seen how to multiply and divide, the basic stuff. Most of the time, if you go through Python code, you will find that these operators right here, multiply, divide, modulo, integer divide, plus and minus, and the two operators on lists, the range and the index, and this one where you have a class, those operators get used more than 90% of the time in all Python code. I went out and pulled out a bunch of Python code from GitHub, several million lines of it, profiled it. Those operators are the ones that get used. Are these others used occasionally? Yeah, there's some utility to them. But that doesn't mean that you can't use it by look it up and go say, okay, I really need to do this. I understand it has an operator. What was that operator? Oh, it's in the precedence table. What does it do? Exactly how does it work? Okay. So that's kind of the last piece of the Python puzzle, is these operators. And there are examples of these in the lecture notes this time, plus this table. So you can go and pull that up, save it, stash it away somewhere and say, yeah, we understand there are a slew of operators and they have an order that they happen in. And I'm better off to use parentheses if I'm uncertain about what order I'm doing. All right, we'll catch you later.